we want to provide a justification to the following relation that correlates the heat capacity at constant pressure with the heat capacity at constant volume. We start from the assumption no change in composition. A number of thermodynamic relations are given. The first two are the definitions of heat capacities. The heat capacity at constant volume is the partial derivative of the internal energy over the temperature at constant volume. Under the assumption of reversible transformation, it can be written as the product between temperature and the partial derivative of entropy over temperature at constant volume. Its units is joule per Kelvin, since we are considering it in this derivation as an extensive quantity. The capital letter C is an indication for that. Similar considerations apply to the heat capacity at constant pressure. We will use also the change of partial derivative rule that is reported here in its general formulation. One of the Maxwell's relations is also needed. The general relation between Cv and Cp includes the coefficients alpha and k. There is a double advantage in using them. First, they are quantities measurable experimentally. Second, these quantities can be calculated from the equation state. Alpha is the coefficient of thermal expansion and is defined as the product between the inverse of the volume and the partial derivative of the volume over temperature at constant pressure. Its unit is 1 over Kelvin. K is the coefficient of isothermal compressibility and is minus the inverse of the volume times the partial derivative of the volume over pressure at constant temperature. Its unit is 1 over pressure expressed in Pascal. Finally, we will make use of the chain rule applied to the volume when it is a function of temperature and pressure. We use the mnemonic rule upstairs, downstairs, outside as follows. We prepare the three ratios first, then we start with V, move to T, and finally to P. We have now everything needed to demonstrate the relation. We start from the expression of Cp as a function of the partial derivative of entropy and write that the ratio Cp over T is equivalent to the partial derivative of entropy over temperature at constant pressure. Now we use the change of partial derivative rule. S will be the x in the general expression, T is A, and P is C. The remaining variable V among P Vt is of course B. We develop the partial derivative by following the rule. The first addendum obtained is the ratio between Cv and T. The last term, the partial derivative of V over temperature at constant pressure, is the product between coefficient of thermal expansion and volume. According to one of the Maxwell relations, as we have noted here, the remaining term is the partial derivative of pressure over temperature at constant volume. Let us write the expression we have obtained so far. The remaining term is the partial derivative of pressure that we need to develop further. To do that, we use the chain rule applied to V as a function of T and P, which embeds also this partial derivative. We explicit now the term. The numerator of the relation obtained is the product between volume and alpha. The denominator is the negative of the product between volume and K. We conclude that the partial derivative of the pressure over temperature at constant volume is the ratio between alpha and K. This term has a certain importance in thermodynamics. The term is used in the thermodynamic equation of state that we have met for the first time by combining the Maxwell's relations with the fundamental equation of thermodynamics written in terms of internal energy. Now we can finally write the general expression relating CD and CP as the difference between CP and CV is the product of temperature, volume, and the ratio between the square of the coefficient of isothermal expansion and the isothermal compressibility. Try yourself to use the ideal gas equation of state in this relation.